Hello everyone and welcome. Today we're diving into the world of input-output scheduling, specifically how operating systems optimize disk access. Input-output scheduling is a crucial aspect of operating systems. It greatly impacts system performance by efficiently managing requests to read from or write to the disk. In this video, we will look at some input-output scheduling algorithms. We'll explore various disk scheduling algorithms designed to minimize head movement, maximize disk throughput, reduce response time, and ensure fairness among processes. These algorithms play a vital role in determining the order in which disk requests are serviced. We will cover first come first served, or FCFS, shortest seek time first, or SSTF scan, also known as the elevator algorithm, and circular scan, also known as C-scan. Let's begin with the basics of disk scheduling. Disk scheduling is essential for several reasons. Firstly, it minimizes seek time, which refers to the time it takes for a disk's read or write head to move to the correct track to access data. Secondly, it maximizes disk throughput, which is the rate at which data can be read from or written to the disk. Thirdly, it reduces response time for input-output requests, ensuring that processes receive the data they need in a timely manner. Lastly, it ensures fairness among processes, preventing any single process from monopolizing disk resources. Here's a simple illustration of a disk. A typical disk consists of multiple tracks, each identified by a unique number. In this example, we have tracks ranging from 0 to 399. The disk head is currently positioned at track 200. Let's discuss the first come first served, or FCFS, disk scheduling algorithm. This is the simplest disk scheduling algorithm. Requests are processed in the order they arrive. While it is fair, it is not optimized for performance and can cause arm thrashing with random requests. Arm thrashing refers to excessive movement of the disk arm, resulting in increased seek times and decreased performance. Here is a pseudocode representation of the first come first served algorithm. While the request queue is not empty, get the next request, move the disk head to the track specified in the request, and process the request. Here's an illustration. In this scenario, we have 4 requests: track 98, track 283, track 37, and track 199. The arrows indicate the movement of the disk head to service each request. Now let's calculate the total head movement. From the starting position, the head moves 98 tracks to reach the first request. Then it moves 185 tracks to reach the second request. Next, it moves 246 tracks to reach the third request, and finally 162 tracks to reach the last request. Adding these values together, we get a total head movement of 691 tracks. Next, let's explore the shortest seek time first, or SSTF, disk scheduling algorithm. Shortest seek time first selects the request closest to the current head position. It minimizes seek time compared to first come first served. However, it can cause starvation for requests far from the head. It is considered a greedy algorithm because it always makes the locally optimal choice. Here is a pseudocode representation of the shortest seek time first algorithm. While the request queue is not empty, find the closest request to the current head position, move the disk head to the track specified in that request, process the request, and remove it from the queue. Here is an illustration. Our disk head starts at track 150. The requests are on tracks 98, 199, 283, and 37. Using the shortest seek time first algorithm, the disk head first moves to track 199, since it is the closest request. Then it services track 98, followed by track 283, and finally track 37. Now let's calculate the total head movement. Moving from the starting position to track 199 requires moving 49 tracks. Then moving to track 98 requires 101 tracks. Moving to track 283 then requires 185 tracks, and moving to track 37 requires 246 tracks. Adding these values together, the total head movement is 581 tracks, which is more efficient than the 691 tracks required by first come first served. Now let's examine the scan algorithm, also known as the elevator algorithm. In this approach, the disk arm moves in one direction until it reaches the end of the disk, servicing requests along its path. Once it reaches the end, it reverses direction and continues servicing requests in the opposite direction. This reduces the arm thrashing problem, as the disk arm moves in a more organized manner. Here is a pseudocode representation of the scan algorithm. The scan algorithm first moves to the end of the disk, servicing each request along the way. After reaching the end, the disk arm reverses direction and services each request on its way back. Here is an illustration. The head starts at track 150. The disk head continues downward, servicing tracks 199, 283, and 399. At the end, it reverses direction and services tracks 98 and 37. Let's calculate the total head movement. Moving from the starting position, the head moves 49 tracks to service track 199, then 84 tracks to service track 283, then 116 tracks to service track 399. At the end, the head reverses direction and moves 246 tracks to service track 37. Adding these up, the total head movement is 495 tracks. Now let's explore the circular scan or C-scan algorithm. This is a variant of the scan algorithm. The head moves in one direction only. When reaching the end, the head jumps to the beginning of the disk. This provides more uniform wait times than the regular scan algorithm. Circular scan treats the disk as a circular list of tracks. Here is an illustration. With circular scan, the head starts at track 150. It continues downward, servicing tracks 199, 283, and 399. At the end, it jumps to track 0. Then it continues to service tracks 37 and 98. Here's how we calculate total head movement. Moving from the starting position, the head moves 49 tracks to service track 199, then 84 tracks to service track 283, then 116 tracks to service track 399. Then it jumps to track 0. Then, it continues to service tracks 37 and 98 for the head movements of 37 and 61 tracks, respectively. Adding these values together, the total head movement is 347 tracks. Now let's compare the algorithms we've discussed. Here's a table summarizing their key characteristics. The first algorithm, first come first served, has poor seek time performance but excellent fairness, and does not cause starvation with an order 1 complexity. Shortest seek time first offers good seek time performance, but poor fairness, and can potentially cause starvation, with an order n complexity. Scan provides good seek time performance and fair fairness, with limited starvation, and an order n complexity. Circular scan offers excellent seek time performance and good fairness, with limited starvation, and an order n complexity. Here are the results for our example request sequence. Circular scan is the most efficient with 347 tracks, followed by scan with 495 tracks, then shortest seek time first with 581 tracks, and finally first come first served with 691 tracks. Now let's delve into some real-world considerations for input-output scheduling. Modern input-output scheduling incorporates various factors to optimize performance. Priority-based scheduling allows critical processes to be prioritized, ensuring they receive timely access to disk resources. Deadline-based scheduling is used for time-sensitive input-output requests, ensuring they are serviced within a specified time frame. Input-output request merging combines adjacent sectors into a single request, reducing overhead and improving efficiency. Anticipatory scheduling anticipates read and write patterns to optimize disk access. Multi-queue scheduling is employed in multi-core systems to distribute input-output requests across multiple queues, improving parallelism and overall performance. The evolution of storage technology has also influenced input-output scheduling strategies. Hard disk drives, or HDDs, rely on mechanical components and are sensitive to seek time, making traditional algorithms applicable. Solid-state drives, or SSDs, have no moving parts and offer random access capabilities, but where leveling becomes important to prolong their lifespan. Non-volatile memory express, or NVMe, drives are ultra-fast and support parallel access, reducing the relevance of traditional scheduling algorithms. Cloud storage introduces distributed storage with network latency dominating performance, necessitating different algorithms to optimize data access. In summary, we've covered several disk scheduling algorithms, each with its own characteristics. First come, first served is simple but inefficient. Shortest seek time first offers better performance, but can potentially lead to starvation. Scan reduces arm thrashing and offers better fairness. Circular scan provides more uniform wait times and is often considered the best overall choice. When selecting a disk scheduling algorithm, it's essential to consider the workload type, storage technology, system requirements, and application needs. Thank you for joining this video. Now, do you have any questions? If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.